Alright, so suppose something and let's prove something else. So we're gonna give the order of h and g a name, or the index, whatever, n, and we're gonna call the order of h k. Then we know that g is kn. Also, if n equals 1, then n equals 1 would imply that h equals g, so n is strictly greater than 1 because h is a proper subgroup. Let g act on subgroups of g by conjugation. And you should prove that this is actually a group action, but it's kind of obvious. If you take any subgroup h of g, then letting one act on h will just give you h, and then just letting the element g1 times g2 act on h will be the same thing as letting because let's see here, g1, g2 acting on h will give you all things of the form g1, g2, h, where h is an h. And that's certainly going to be equal to g1 times, or rather it's going to be equal to g1 times g2h for all g2h in g2h. And so that's equal to g1, g2h. And so you have that, and then that confirms that we are in, or that we have defined a group action. So you can do that, like you can write it out if you want, but I'm just going to leave it at this. Conjugation. So now the stabilizer, and I like to put this g down in the bottom here because first of all I learned how that's how it was introduced to me. The other thing is that it helps you keep track of everything that's going on because there's so many little details flying around everywhere. I mean, it is pretty obvious in this problem that the overarching group is G, but I don't know, I prefer to be more explicit. So the stabilizer with respect to this action is all elements of G such that conjugation fixes it, but that's precisely by definition the normalizer of H, of the set H. So by orbit stabilizer theorem, which I don't think is called by name in Jacobson's textbook, but I mean it's stated there. Basically OH, and that's the orbit of the subgroup H under the action of G on subgroups by conjugation. Well, the theorem tells us that this is equal to the index of the stabilizer in here, but this, of course, we know is just G and GH. But what is this? This is going to be, let's see here, we know that order of G is equal to G mod G index H times order of H, and so you can just divide the order of the subgroup on the side there, and so what you're going to get is you're going to get the order of G divided by the order of the normalizer. Now, we want to get a bound on this. See, I like this. This is analysis. We're doing inequalities. So anyways, so G is equal to Kn, and we don't know how big Ng of H is, but we do know that it contains all of H, because obviously if you take something in H, so basically for all little h and big H, big H inverse is equal to H. And so certainly the normalizer of H contains H, and so this denominator here is going to be bigger than or equal to K, and so if we're dividing, then it's this whole fraction is going to be less than or equal to this, and then divided by K, which is the smallest possible value of NGH. But what is this? This is just N. So there we go. We know that 1 is contained in GHG inverse for all G and G, or rather, so here, this is for every conjugacy class. Basically, anytime you have a conjugacy class, it will contain 1 because H contains 1, and so if you take any G, then G1, G inverse is just equal to 1. So what does this tell us? So if we take the union for all elements G, little g and G of GHG inverse, or the conjugacy class, or whatever, this is going to be less than or equal to. Now we know that there is going to be one of these conjugacy classes is going to be let's see here, is going to be associated with just the element 1. Right. Hold on. Let me write out what I have here real quick. Then see if I can remember why I wrote this. So this n times k minus 1, basically what this, oh yeah, of course. So the order of this union, so every single one of these, or certainly every single, rather this should say, not just for every conjugacy class, for all G and G. So this is less than or equal to, now for every single G, right, so for every single G and big G, you're going to have the element 1. And so we're going to count that here. So this, the norm of this is at least 1 because it contains the element 1. But then how big could the other conjugacy classes possibly be? Worst case scenario is that, let's see, we have the orbit of H is equal to, is less than or equal to n. So we have at most n different conjugacy classes, distinct conjugacy classes that we get from taking this union. And in each conjugacy class, the only thing we know is we know it contains 1. And it can't be any bigger than the size of H, obviously. So it's this k minus 1 accounts for the other possible elements of each conjugacy class. And so that's where these numbers are coming from. And so this is less than or equal to this. But this is, you just do some math here. K minus n minus 1. And this is strictly less than nk because n is strictly greater than 1. So this is a strictly this number here is strictly less than 0, and so it's definitely bringing this down. So we have a strict less than nk, and this is the order of G. And so the number of elements in this union is strictly less than the number of elements of G, and so hence this implies that it must be the case that G is not the union of this. And there we go. This completes our proof.